All right, this is a diode problem, and what we're going to do is use the ideal diode model to solve for the voltage Vx. Vx is measured with respect to ground. So we have to make an assumption about the diodes. They're either going to be forward biased or reverse biased. I'm going to assume that they're both forward biased. I think that assumption is a good one because it's easier to check the assumption. Once we calculate the currents in the circuit, if the current through this diode is in that direction, then our assumption is correct. It is forward biased. If the current is in this direction through this diode, then our assumption is correct with that diode. If we found that the current was going up here, then that's impossible for a forward biased diode, and that would mean our assumption is incorrect. So what we're going to do is replace the diodes with the forward bias model, do our calculations, and then check our result. So what I'm going to do is, let's call this diode D1 and this diode D2. What I'm going to do is assume the forward bias model, which is a short circuit. Same thing here, short circuit. Now I'm ready to make my calculations, and this is set up nicely for doing nodal analysis because I've got a voltage up here, Vx. Remember, this is a short circuit, so the voltage throughout the whole thing is Vx. And I think with the one nodal equation, I can solve for Vx. Let's go ahead and do that. Summing the current leaving this node would be -4 plus Vx over 1K. That's this current. This current is Vx over 10K. This current is Vx minus 12 over 2K equals 0. And now we're going to solve this for Vx, and the easiest way to do that is to form a common denominator. I think everything will be, let's see, if I multiply top and bottom here by 10, that would give me 10 Vx over 10K, etc. So when I do that, I get -40 plus 10 Vx plus a Vx plus 5 Vx minus 60 equals 0. Solving for Vx, let's see, I've got 10, 11, 5, 16 Vx, 16 Vx equals 100. So Vx is equal to 100 over 16 volts. So that's my answer, but I made an assumption about these diodes that they were both forward biased. I have to check to make sure that assumption is correct. So let's figure out this current. This current, I'll call this ID2, would be Vx divided by 10K, and I'm going to get a positive number. So ID2 is equal to Vx over 10K, which is 100 over 16 divided by 10K, and I'm going to get 10 over 16 milliamps, and it's positive. ID2 is greater than 0, therefore D2 is forward biased, and my assumption for that diode is correct. Now we'll look at D1. Is that forward biased? So I need to make sure that the current is going in this direction, because if you recall, this was the orientation of this diode. This diode was like this. So is this current positive? So how do I figure that out? Well, I could do KCL at this node I know that this voltage is equal to 100 over 16. So let's do KCL at this node, at that point. I'll call that point Q. So KCL at point Q, KCL at Q. So summing the current leaving that node, what I get is -4 is leaving, going this way. The current going this way is Vx over 1K plus this current, which I'm going to call ID1 plus ID1. So we'll solve for ID1, and what we get is ID1 is equal to Vx over 1K. Vx is 100 over 16. So that'd be, actually solving for ID1, so I'm going to have, putting this over there, we'll have 4 minus Vx over 1K. So that'd be 100 over 16. And well, in order to make this all work, this had to be in milliamps. So let me make that correction. Now it is correct. Vx over 1K would be, here's Vx divided by 1K, that makes this in milliamps. This would be milliamps, so we have 4 minus this. And what we get, this is going to be 100 over 16 is, it's around 6 milliamps. So it's going to be a negative number. So ID1 is less than 0. Therefore, this is reverse biased. I assumed it would be forward biased, so my assumption is incorrect for that diode. So I'm going to have to rework the problem. And now what I do is I'm going to assume that this is reverse biased. This is forward biased. And now solve for Vx. And since this is an open circuit, I just have the 2K and the 10K in series, and so I can use voltage division to find Vx. So Vx is equal to 12 times 10K over 10K plus 2K. And what I get is 10 volts for Vx. You could do this in a Java circuit simulator and you would get the same, you wouldn't get the same result because the diodes are not treated as open and short circuit like the ideal diode model we're using. They're using something more like the constant voltage drop model. Actually, they're using the Shockley equation, which is a little more complicated still, but you'll get close to the correct answer if you try to simulate this. So to review, the first step is to assume a state for the diodes. And I recommend that you assume that you've got forward bias diodes. You do your calculations and then test whether the diodes were in fact forward biased. If they're forward biased, the current has to be going through in the forward bias direction. If you find that one or more does not follow that convention, then that means that your assumption for that particular diode was incorrect and you rework the problem under the new scenario. So I found that this diode was reverse bias, so I replace it with an open circuit because that's the reverse bias model, and then do the calculations. All right, I hope that helps. you understand the procedure for doing ideal diode model calculations.